Hello, everyone. Today, I will continue the series of sampling lectures and talk about new sampling methods called rejection sampling and importance sampling. So previously, we talked about the inverse transform sampling based on the grid sampling. And in the second lecture, we talked about how to use the idea of the grid sampling to sample from Gaussian distribution. So in this talk, we'll basically talk about rejection sampling and importance sampling. And these two sampling methods are both based on the idea of sample and then correct. So the idea is that we first want to sample in another distribution, and we want to make the correction so that the resulting samples follow the original distribution we want to sample. Okay, so just to as a recap, we basically want to see what's the requirements for sampling from a specific distribution P of X. So when we talk about sampling from P of X, we actually talking about sampling, generating samples such that the probability of selecting any sample is proportional to P of X. So for example, the probability of sampling x1 is proportional to P of x1, and also probability of sampling x2 is proportional to P of x2. So the probability of sampling x1 versus x2 is equal to px1 divided by px2. So that's something we want to check for every method we are going to talk about. So once this condition holds, then our sampling method is correct. So the general idea for sample then correct is as follows. So first, we want to sample in a distribution P of X. That's our target distribution. It may not be easy to sample, so we want to sample on a different distribution Q of X, so which is easier to sample in this case. So because it's easy to sample, we can easily generate sample from Q of X. And then we want to do the correction such that the resulting sample follows P of X, which means we follow this specific condition. Okay, so let's talk about sample, how we want to correct our samples. So first way to correct that is to use the reweighting. Okay, so for example, for any sample x1 following the distribution Q of X, we assign weight which equal to P of x1 divided by Q of x1. So by doing this, we basically do the correction such that the weighted sample probability follows following condition. So basically, the probability of weighted probability of sampling x1 equal to its weight w1 times the sampling probability in x1, which equal to px1 divided by qx1 times the sampling probability q of x1, which equal to px1. Similarly, the weighted probability of sampling x2 equal to p of x2. So we verify that this condition holds, which means that the weighted sample follows our original distribution P of X. So we can see an example here. So for x1, we can see that P of x1 is equal to 0.5, Q of x1 equal to 1. So for sample x1, we wanted to basically assign weight 0.5 to this sample. And also for x2, we see that P of x2 is equal to 1.2 and Q of x2 is 0.4. So the weight for x2 is 3 in this case. So in this case, we once we assign weights to these samples, we basically ensure that the weighted sample probability follows original distribution P of X. So this is basically the idea of the importance sampling. So we assign importance to each sample and then just use that importance weight to do the correction. And as we will see later, the main motivation for importance sampling is to reduce variance, and which is basically the a lot of other textbooks and other videos talk about that as the main motivation. We will see that later. The second way we want to do the correction is to discard some samples. We don't want to keep all samples from Q of x. So, for example, we can define the weight to keep the sample, to accept the sample, as the weight px divided by qx. For example, in the previous case, we can see that for x1, the weight here is 0.5. So we want to keep the sample with probability equal to 0.5, which means that we discard the sample half of the time. So for x2, because the weight here is 3, which is greater than 1, so we don't use this method because we can't define the probability of accepting the sample as 300% yet. So in this case, we decided to keep the x2 as the weighted probability as we did before, but for x1 we decided to keep x1 with probability 0.5. So now the ratio between the probability of getting these two samples is equal to this one. So in the numerator, we see that it's equal to the probability of accepting the sample times the probability of getting the sample from qx1, and which equals to px1 divided by qx1 and times qx1 also equals to px1. And for denominator, we can see that as previously shown, it is equal to px2, so this condition still holds. So we can see that by discarding some samples, we can still get the correct distribution. Okay, so let's talk about the case when the weight wx greater than 1. For example, in this case, w2 equal to 3. So how do we discard samples if it's like it have the weight greater than 1? To do this, we can introduce a constant c such that for all x, this ratio px divided by cqx is smaller or equal to 1, so that we can define the probability of accepting the sample to be this value. So for example, in this case, we can define c equal to 10, such that the probability of keeping x1 equal to 0.05, and probability of accepting x2 is equal to 0.3. Okay, so by doing this, we can still show that the following condition holds. So probability, the ratio of probability of getting x1 versus x2 equal to the probability of accepting x1 times sampling probability of qx1. So this part equal to px1 divided by cqx1 times qx1, and which is proportional to px1. And also in the denominator, we also have the probability of getting x2 equal to proportional to px2. So this condition still holds, which means that after discarding some samples, the remaining sample will follow the distribution of px1. So that is the idea of rejection sampling. We are basically saying that we want to sample following the distribution of Q, and then reject specific samples, and remaining samples will follow original distribution P of x. As a quick recap, so we go over these two sampling methods: importance sampling and rejection sampling. So both sampling idea want to sample from a distribution P of x. So to do that, we basically want to generate samples from an easy to sample distribution, Q of x in this case, and then we want to do the correction for samples. For importance sampling, the correction method is to do the reweighting. We apply the weights equal to P of x divided by Q of x. And in rejection sampling, we want to discard some samples and keep the remaining sample with the probability of Px divided by Cq of x. So yeah, so that's two different correction methods, but the idea is very similar. Okay, so as we talked about in previous slides, we say that importance sampling is mainly used to reduce the variance. So let me give you some example. For example, if we want to compute the expectation value of P of f under the distribution P of x, which is the basically taking this integral P for fx times px over x. And this integral can be estimated using this average. Basically, we want to take n samples from P of x as xi, and then take the average of the f values at these endpoints and take the average. So the problem of doing this average is that, for example, if we have a fx which has a very sharp peak in this case, then a lot of samples, if we sample in this kind of regions, then the values will be very low. For example, if n equals 3 here, meaning we want to sample 3 points to estimate this expectation, then if all the 3 points fall under this low or sample from this low value region, then the expectation value will be very, very low. But if these 3 points are sampled in this high value peaks, then the expectation will be very high. So that means that the selection of samples will cause a big difference in for the expectation estimation. So the estimation will have a very big variance in this case. So to fix that, instead of sampling in original P distribution P of x, we want to sample from a different distribution Q of x, which is related to importance sampling. Basically, we want to sample from Q of x, and then we use the weighted value. Here, the weight is proportional to P of x divided by Q of x. And the weighted value is just the f is the P over Q times f. And then the sample is generated from distribution Q of x. And if the Q of x is properly chosen, then we can see that P f over Q is a much smoother function in this case. Then if we have different samples in different regions, we can expect that the variance for the expectation estimation will be much lower. So if we write it down like this, the variance of the of fp over q when x example from qx is much lower than the variance of f when x follows the distribution of p. So yeah, that's the main reason why we want to do importance sampling, and this is very commonly used in a lot of realistic sampling, because a lot of distributions are severely peaked around some kind of high probability regions. So a lot of samples will not contribute to this integral. So sampling in those low value regions will not be too efficient, and also it will cause a lot of large variance in this case. So in that case, we want to use a weighted distribution to reduce the variance. Okay, that's all we want to talk about. Basically, we covered two distributions, two sampling methods, importance sampling and rejection sampling. So both methods are based on the idea of sample and then correct. So we sample from an easy to sample distribution and make the correction by either reweighting the samples or discard some samples. So this is a very efficient way to do the sampling. and is used widely in practice. Okay, so let me know if you have any questions. Thank you so much for your attention.